to introduce Professor Jens Chluba, and Jens got his PhD from MPA at 2005, and immediately he did a postdoc at the MPA, and then he actually moved here in 2008, and so I'm still at them. We didn't come within us. So until this end of this month, right?
Just until Thursday. Thursday.
Oh, it's Thursday. Actually.
So end of the month in some.
End of month.
In some metric.
And yeah, and then he moved to Cambridge, and then finally moved to University of Manchester as a professor. And today he will talk about the science with spectral distortion with the CMB. So take away.
Yeah, thanks a lot. I'm extremely happy to be back. It has been many years that I have been here. At least 10 years ago, I think, is the last time I visited, and I'm really happy to see so many new faces and young people at CITA with the level of activity that I'm just used to, and it's really a great visit so far already. Have been well fed as well, so excellent. So today my talk is going to be, I'm going to try to tell you why spectral distortions of the microwave background are really interesting to think about. And I think CITA is also one of the places that I should have come much earlier to talk about this, because there's so many people working on this topic here that could get involved in helping with the challenges that we have to overcome. So I hope at the end of my talk, some of you will be saying, oh yeah, cool, let's sign up for this. Okay, so spectral distortions, what are they about? This is fun. Probably just, oh, this is recorded, that's the reason. Good. Okay, so this is a map that many of you have, you have all seen this, right? It was CMB anisotropies. We have learned a lot about the cosmology we live in, the universe we live in, by looking at the statistics. I could talk about this, or one could talk about this a very long time, but this is not going to be the topic of something else, yeah. This is not going to be the topic of this talk. So CMB anisotropies, completely forget about them. Everything that I'm going to talk about is, or mostly everything that I'm talking about is about the monopole. Why is it? This will be a bit choppy because I'm switching many times. Everything is about the monopole. This is the sky signal that I'm looking for. The average sky flux of photons coming from the Big Bang and the energy distribution of these photons. So this is really going to be. Let's start the sharing again, because somehow it's going back and forth for some reason. Okay, excuse me. Share. All right. This guy. Technology. Let's see if this works now. And Kobe-Virus has shown us that the microwave background spectrum is really extremely close to a black body, that of a black body, with a temperature that's precisely measured. And here the theory curve is covering the thickness of the error bars. The thickness of the theory curve is just covering the error bars. This is a precise measurement. Received the Nobel Prize in physics. This is a unique measurement of demonstration of a thermal hot phase in the early universe. But there's these parameters mu and y, which are the standard spectral distortion parameters, and I'm going to try to explain a bit of the physics behind them in what follows. But let's just for now move on. And the Y-type distortion is a type of distortion that we're familiar with, and also in connection with the Sunyaev-Selvidge effect. So when you have hot gas in clusters of galaxies, you get the CMB that comes in and is upscattered by the just energy transfer from the electrons to the photons. And this scattering happens in the inefficient scattering regime, where you just partially upscatter photons. And this process in the early universe, there's an equivalent of that, which happens basically at any time below redshifts of 50,000. So low redshifts, which I call low redshifts. Of course, you guys are looking at galaxies. Redshift 10 is a fairly high redshift. For me, 50,000, which is roughly a couple of thousand years after the Big Bang, that's what I call low redshifts. When you go to the early universe, at higher redshifts, interactions in the plasma become quicker, and you have you can equilibrate essentially the CMB photons and the electrons in terms of energy exchange. But if you want to establish a black body spectrum, you also need to change the number of photons. Once you have injected some energy, for example, or change the equilibrium, you need to adjust the number of photons to really reestablish the T⁴ and T⁵ scaling of number density and or energy density and number density. This is a process that takes time, and in the early universe, that's one of the reasons why you can actually see spectral distortions at the end. So, but when you're in this high redshift regime where you get a lot of scatterings, you get the so-called chemical potential type distortion, the mu type distortion, where the number of photons is fixed, but the energy distribution is something that you can adjust. So you have all of a sudden two parameters that you can play with. And the second parameter is the chemical potential. The black line is here, the black solid thick line, that's the chemical potential distortion. I will show this in some other versions in a second, which is making it slightly clearer.
So you're going to explain to us the extent to which emission at a very different wavelength than the CMB peak can be convincingly ascribed to the primordial universe as opposed to foregrounds.
I will try to talk about that at the end as well, but you are bringing up a really important point. If we see a mu distortion, that is a distortion that comes from the primordial universe. There's no way to make a mu distortion, a mu-type distortion at late times.
If it mathematically follows.
Mathematically, yes. But we have, you know, just like with all our analysis techniques from CMB anisotropies, we are knowing how to do foreground analysis and actually model the universe, and that's one of the big challenges, of course, how you need to get to the very early universe signals. Okay, so this is a figure that also most of you have seen. So we're of course studying the universe as a whole, the history of the universe. With the CMB anisotropies, we're usually, you know, interested in learning about the initial conditions set by inflation or the early universe physics by looking at the maps from the last scattering surface, studying the anisotropies. That's the science we're doing. And then, of course, there's lots of interesting things happening at late times with secondary CMB anisotropies or B modes generated by scattering physics and so on, lensing effects. All this is really fun science, but spectral distortions are, I don't know why it's doing that. Spectral distortions are about probing the thermal history of the universe, looking at basically energy release processes across the history of the universe, starting from a couple of months after the Big Bang until today. Right? So when you have energy release processes, you can change the spectrum, and when you do this late enough, you will see a distortion today. So the standard picture with the mu and y distortion that I just explained, this is going to be really fun. Let me see if this is better. No, it's something is not communicating right. I'm really sorry about that. All right, let me see if I can, but I think it's actually a Zoom issue. I was just complaining how Zoom is changing every time you start it. It's like update, update, and then I think this is probably one of those. Potentially, I just updated, so I don't know if you have the latest version of Zoom. Anyway, so spectral distortions are sensitive to energy release throughout the history of the universe, and this opens a way to look into the pre-recombination universe, because you can actually sense energy release and non-equilibrium processes during the pre-recombination universe. The standard picture that I already explained, the mu and y-type distortion, is this, you know, early universe distortion in the mu era, late universe distortion in the y era. That's the standard picture, the classical way of thinking about distortion science. And you can estimate the amplitude of these parameters just by knowing how much energy was really deposited during these eras, right? So I mentioned 50,000, redshift of 50,000, and then the mu era, the full thermalization happens at earlier times, even like before three to a couple of months after the Big Bang, and that's corresponding to a redshift of something like 2 million or so. So this picture has been refined in the recent years to also understand that the transition between the mu and y era, of course, is not just abrupt. There is actually a gradual transition. And the important thing is that the signals that are created during this transition are not just the sum of mu and y or temperature. They actually contain time-dependent information. So you can really learn something like a third dimension into the spectrum. You can actually learn time-dependent, get time-dependent information from measurements of the spectrum. And there's also the hydrogen and helium recombination lines, which are much more featureful, as I will show, which in principle tell you about processes going on there and give you another way of time slicing. Okay, we now have codes to really treat these thermalization processes very accurately. Cosmotherm is the code that I wrote, and I have been promising it to make it public actually for many years. But you can have it if you just talk to me. The reason why it's not out there is just it was in such a state that it wasn't really presentable to anyone. But it's now really a nice tool which includes many energy scenarios and is actually used to predict distortion signals in an accurate way. And we include accurate description of quantization. We include accurate descriptions of Bremsstrahlung and double Compton processes. These are all like the microphysical processes that really are mattering for the anisotropy calculation. But I don't want to go into details, of course. And beyond standard energy release distortions, which is the way you estimate normally, you also can, of course, imagine injecting photons, for example, the recombination lines, and these depending on when they happen, in which era of the universe, and where they happen, they will actually lead to distortions that can look much more rich than the standard mu-type distortion and y-type distortion. Okay, so I've been giving you just a very vague idea of what distortions are, but let's first ask the question: why is this even interesting? These numbers here that tell us that there is no distortion, nothing interesting to see. So why am I even talking, right? So the first reason is that there's a quite long list of processes that you can think about that will lead to distortions. So this figure is pretty busy, but here's redshift, so this is again the time. The signal changes, basically, the early signal is like temperature changes or ineffective changes, then the mu distortion, and then the residual distortion error. So you have this time-dependent information, if you will. And then you can think of the y-axis here as a sensitivity axis. So here is the sensitivity that Virus had, and it's just a simple statement that Virus was not sensitive enough to see even expected lambda CDM distortions. So encoded here in yellow, I have those which are lambda CDM distortions. They are not new physics. They are just standard distortions that should be there. And if you have enough sensitivity, you will be able to get them. And I will briefly mention here the realization and structure formation distortions. Then the dissipation of acoustic modes, which is, I think, one of the really interesting targets for future studies of the early universe. And then also the recombination lines, which are, those I will try to explain and highlight some of the physics you might be able to do. But then there's a wide, there's a list of distortion scenarios that are, if you look at this is just physics that everybody's talking about. Primordial black holes, axions, magnetic fields, I mean, you name it. So spectral distortions can shed light on these scenarios when you measure them. Okay, so that's exciting. And of course, it's important to realize as well that our current state is still spectral distortions having been measured 30 years ago by Virus, or constrained 30 years ago. But in terms of experimental progress, we can not only imagine many incarnations of improvements over the Virus measurements, but we can also, we are even now starting to develop from the ground, and also with balloon-based ideas, actually concepts that will be able to push the frontier forward slightly. I'm going to mention in particular Visu, which is a French-led balloon mission, or a balloon experiment, which is really looking very likely that it will go into phase A next year, which means that it will potentially be operating on a timescale of a couple of, maybe 5 years from now, which is really interesting, and it would be seeing some of the distortion signals that are guaranteed. And then there's also TMS, which is the Tenerife microwave spectrometer, which in fact is starting to measure probably this summer, or in the later this year. And that would be able to see some signals that are also predicted at low frequencies. Okay, so of course one can go arbitrarily ambitious. So for example, ideas like seeing Barat and going to the moon. You guys probably have also talked about astronomy from the moon. This is some ideas in which you can in principle also think. But the bottom line is really there's lots of concepts out there that could in principle measure, push the frontier forward from the 30 years back state. Okay, so I've talked about PIXI and mentioned it, and PIXI is really the strongman mission concept for all these measurements. So let me try to highlight a little bit how this works. So PIXI was first put forward in 2011 as a mid-X mission, and it wasn't even that expensive at the time, estimated to be of order 200 million. But obviously it is still an ambitious mission, and it had the target of improving the Kobe-Farris constraint by a factor of 1,000, essentially. In terms of raw sensitivity, in terms of control of systematics, this is not a problem. Okay? But of course, it is true, there's like lots of foreground signals and things you have to take care of to really get to these signals. Nevertheless, this was one of the big targets of PIXI, and then also measurement of B modes in principle to the level comparable to what is now, name of the game as well. Just to highlight, PIXI works like this. You have two basically optics, two barrels that look at the sky, and when you are differencing these through a sequence or optical path, you can in principle get an interferometer of the sky's spectrum. So this is really a Fourier transform spectrometer, which is used, very routinely nowadays in labs to do really spectroscopic measurements. If you put a calibrator in front of one of these barrels, then you can absolutely measure the sky flux relative to the calibrator, and in principle do an absolute measurement to get a spectrum. So this is how this normally works in terms of the principal concept. And multiplications of PIXI or changes in the setups of the optics, that's basically all these different kind of designs that people are talking about. So this perspective has stimulated a lot of activity over the past years. There was workshops on distortions. Here's one that we had at CERN, where lots of people were contributing and discussing what is the science, how you can get ready for this. And then we had a sequence of white papers just a couple of years ago now, which highlighted all the incredible science that you can do with spectral distortions. And I'm going to highlight this in a second as well. In Manchester, we had a pretty big gang. It's now trickling down because unfortunately funding doesn't go on forever in the real world. But we have had a range of different directions in which we work, in particular also related to foreground questions, how you can actually subtract these things, and predictions of signals and so on. And I think one of the great outcomes of all that work is that spectral distortions, at least within Europe, within ESA, have now been recognized as one of the potential targets or potential contenders for the new physical probes of the early universe category in the ESA 2050 program. So this is a pretty long time scale. We're talking about 20, 30 years from now. But it is unfortunately also the time scale that when you really start some experimental activity from space, that is really the kind of time scale you're talking about. And it is, of course, now time to really start thinking about it and getting involved. And this is one of the things that we have, recently we had another workshop just thinking about how we can get involved and organized. And it's really, time now to talk about this. Okay, so this was all broad brush propaganda. Okay, let's now talk about some specific distortion signals so that we can actually get down to the science. So let's focus on the lambda CM distortions. The largest distortion is just the Y-type distortion. Here I'm showing the distortion signal in the logarithmic scale because we are going to see a big dynamic range. And this is nothing else than the Y-type distortion with the characteristic null at 217 gigahertz. So just the compensation of the CMB background, upscattering. So you get removal of photons here at low frequencies, and then you get photons appear at high frequencies. This is essentially just all the hot gas in the low redshift universe, and the expected signal strength is something like 2 times 10 to the minus 6. 1.5 times 10 to the minus 6 was what virus at 2 sigma had constrained. So this is roughly 1 order of magnitude below that limit in terms of 1 sigma. This is a signal that, with the sensitivity that Pixie could reach, is really easy to see. Now, Pixie is still a space mission. With a balloon-bound mission, it becomes, you're talking a bit more in the range of here, but this should still be a signal, even after marginalization over foregrounds, and in particular the atmosphere, that should be still visible. So this is one target, and it teaches you about the lake universe. I want to, before illustrating that a bit more, just highlight there is also a relativistic correction to the signal, because the gas that actually leads to the upscattering is hot gas in clusters, and these clusters, they have like several keV temperature, and when you're talking about the Sunil-Sedovich effect, normally that is the non-relativistic regime of scattering, but you can also get into the relativistic regime, and that is leading to another correction to the signal that is actually, again, for a Pixie-type experiment, even after marginalization of foregrounds, you should be able to see this relatively confidently. Yes?
Can ground-based experiments kiss the top of that, or do they?
So this year, Cosmo, for example, with the Italian collaborators are planning something in that direction. It might be able to see something, but ultimately, I think it's clear that one has to go to a balloon to do this, because the atmosphere is so much more severe at low altitudes that this is really going to be very hard to improve dramatically over virus. We're talking at least a factor of 20 improvement over virus to get as reasonable significance detection of this signal, right? But in terms of raw sensitivity, this shouldn't be a big problem. It's all about control of foregrounds and atmosphere. Of course, when you go to space, which is ultimately the goal, you are not having the atmosphere to deal with, but you still have to marginalize over all the emissions from the universe as well. So this is, as Chris is correctly worried about, a big challenge. Okay, so what do you learn when you measure this? Well, here's an illustration of basically the mean y parameter predicted from different simulations that people do versus the mean temperature within these simulations. And you can see the parameter space is really covering a whole kind of range. And it comes, of course, down to the details of feedback mechanisms and the physics of that, supernova feedback, AGN feedback, all the thermodynamics of the gas. With Pixie, or Pristine, which was a simpler, a much smaller, less ambitious, more akin to a Bezout-like spectrometer, but still space, you could in principle be homing in onto is the exact parameter space. So this would be really informing average properties of structure formation, and therefore, be quite interesting in terms of calibrating energy output from the lake universe. So this is a signal that is not uniquely tested by spectral distortions. You can in principle get at the signal in other ways, right? You can look at clusters directly, you can look at X-rays, even if you can make arguments that with spectral distortions you will really take a census of all this, this is not going to drive a space mission, right? But what is really important is the dissipation of acoustic models at small scales. And I'm going to spend some time explaining this because I think this is really one of the absolutely crucial aspects of spectral distortion science. So CMB anisotropies, we know they look like this, and the power spectrum of this, here's an old compilation of Planck data, ACT and SPT. The power drops like a rock at small scales, right? If you, we all know that this comes from diffusion damping, silk damping, and if you were able to undo this silk damping, well, you would get a power spectrum that potentially has some wiggles just from the Doppler terms and so on, but it's basically undamped like the initial conditions were setting, which we expect to be quasi-scaling, right? The conversion of this power into basically the damped power is equivalent to energies, and you get a spectral distortion source. How does this really work microphysically? It's very simple. Think of the universe made of patches with slightly lower and slightly higher temperature. Here's a black body of some higher temperature, here's a black body of some lower temperature. Now, you take the average temperature black body, that would be this black dashed line, and if you take the universe and you just shake the box and mix these photons into one distribution, but without changing the energy distribution, just shaking the box, it's like Thomson scattering, mixing the medium, well, you get the purple line. And in this exaggerated case, you can immediately see that this is not a black body. It's just a statement of two black bodies mixed together. It's not a black body, right? This is obvious. Then you thermalize and you start Comptonizing and you get to leading order. In this instance, you have actually a Y distortion. And then if this happens early on, you get a mu distortion. So this is how this works. This is nothing else than mixing of black bodies is not a black body. Yeah? And that, of course, you can calculate now, given an initial power spectrum, you can calculate what is the signal you expect. And if you just take the data from Planck and put this into the Cosmotherm code, which treats all this dissipated processes properly, you get a prediction of a mu distortion, which is like 2 × 10⁻⁸. This is a target signal that lambda CDM is predicting. If we do not see this signal, lambda CDM is not in the simple incarnation correct. There's something else going on. What it is, that is another story, but I told you already about the residual distortions and all this other information, which we can actually probably use to really nail it down. But I want to stress, this is a number that if we don't find it in this way, we are actually breaking lambda CDM. Okay? So one single measurement that could rule out or test an extrapolation of lambda CDM in a regime that we haven't tested before. Why am I saying in a regime that we haven't tested before? The CMB anisotropies, here's a power spectrum as a function of wave number. CMB anisotropies have, and largely structure, they have probed the power of fluctuations, at the up to, let's say, wave number of 1 inverse megaparsec. Pixie, or a spectrometer, would probe the power spectrum in a regime of several hundred to several thousand inverse megaparsecs. So this is parts of the power of fluctuations that we haven't actually tested. And you guys, of course, have heard about all these talks about primordial black holes potentially contributing some not negligible fraction to dark matter. If you want to create a primordial black hole, this is what this illustration is supposed to give away. You need to have power at small scales that's significantly above the extrapolated level of lambda CDM. But within a model of early universe, and if you assume slower inflation, the steepest you could actually get to this level is going k to the 4. As you can see, this is here the scales that are primordial black holes of several solar masses. If you want to get there, well, you're really close to touching this. And in reality, depending on what model you calculate, you will get constraints from mu distortions, basically at the level of what Pixie is able to do. And I'm talking here about Pixie, again, as the standard kind of version of Pixie, which actually, in terms of sensitivity, would be able to touch this curve even, but because of the foreground marginalization, you lose a factor of 10. So, what is this saying? By wanting to learn about the small scales, you have to get to the small scales, and spectral distortions are going to be one way of testing the small scale power. Here's another version of this. This is something that you probably have seen from the...
Can I just ask a quick question?
Yes, please.
10 to the 6.
Yes.
To that figure. Is that just the transition of Planckian to Bose-Einstein?
No, this is here
So it's not redshift.
No, this is not redshift. This is really so this part here is the Planckian to Bose-Einstein, and yeah. So this Planck, this steep curve, but so this is at 10 to the 5 roughly. That's why.
No, but
yeah.
the point is that for this signal, Virus and Pixie can't go to larger wave numbers than what is defined by the transition from Planck to Bose-Einstein.
That's correct. Yes, because
so that's setting that huge steepness.
Correct. Yes. Yeah. And the modes, they enter the horizon at earlier times, but they dissipate at the redshift of 1 million or below to be probed in this way.
So I get what you're saying about PTA here.
Yes.
And obviously PDHs. But what other constraints do you think are fundamental to the higher K regime?
Well, I mean, obviously you have, for example, if there's a gravitational wave background, you have things like ineffective being affected in terms of like extra contributions to power in tensor modes. You know, again, it is the whole story will be about scalar perturbations and versus tensor perturbations, and I think that will be a very, very big multi-messenger kind of approach that we will have to deal with. One way
I don't have a clear way of putting it on this figure, but I think it's there, which is that reionization, just because of that constraint. Oh, where was that? You pointed to it here?
So here would be like things that you could do with 21 centimeter and so on. You would probably be able to push forward here maybe to the 10s, if you're optimistic, even the hundreds of inverse megaparsecs. That is certainly something one could imagine doing. But it will be very hard to go to 10 to the 4 inverse megaparsecs or beyond. And let me just, maybe I made a mistake showing this old version of figures, but for example, we all have heard about the nanograph stochastic background detection. And one figure in this paper was highlighting the constraint of Firas, where here there was basically just some models discussed, which could, in principle, through secondary perturbations, the scalar-induced gravitational waves, which could be, basically emitting or be originating, leading to an explanation for the nanograph detection, right? These models, one thing that I immediately did is just like put some constraint that actually Dongyi Zhang and Mark Kaminkowski and myself did a couple of years ago with Joseph Bradler as well, where we just said, okay, well, if there's actually dissipation during BBN, you will get an increase in the N effective and therefore also change the nucleosynthesis outcomes, and that gives you a constraint, in fact, which is here. And then Pixie, as you can see, this would be, this is just me drawing a line here, but this is basically where Pixie would be going. You would see those models, and I calculated specifically convolving these models with the distortion signal calculation. You will get like 10 to the 6 of them. This will be 100 times bigger than lambda CDM. So these models could in principle be completely tested and ruled out. Yeah? There's also secondary perturbations which one can talk about. This is some work that I'm doing right now. I'm not going to go into details, but the point is really stories about the small scale power that we're seeing currently evolve and appear. There will be an important ingredient from spectral distortions in shedding light on this and testing the primordial origin of it as well. Because let's imagine there's some black holes that are emerging. Well, that's great. Are they of primordial origin? Well, if they are of primordial origin, well, you will see probably a spectral distortion as well. If you don't see a spectral distortion, that will already lead to some tension in that picture. If you're not even, and also let me stress, this actually rules out primordial formation of supermassive black holes. Right? This is the supermassive black hole window, which has been ruled out by Faras since basically 30 years. So primordial supermassive black holes that we see in the centers of galaxies, that is not a story we can tell because of spectral distortion measurements. Okay, so, and there's a paper coming soon where we actually are going to explain this picture in much more detail, which I think is going to be really interesting. There's also a direct way of measuring gravitational wave power with spectral distortions, just like acoustic modes in the scalar from scalar perturbations dissipate. You actually have tensor perturbations dissipate, and here's just the picture that we all are looking forward to seeing emerge, with the large scales being probed by Lightbird and other CMB experiments, and then the small scales by the various also timing arrays and interferometers and so on. Spectral distortions, they bridge the gap between these two regimes, and in terms of direct constraints, can actually say there can't be direct gravitational wave power at this and this level. Now, you see that, of course, the amplitude is much, much more marginal in comparison to what straight connections between these models would be. But if you have models like out-of-field axions or phase transitions and stuff, you could imagine putting bumps in here, and you would be directly testing this with spectral distortion. So this will be still a very important way of looking at these scenarios. And the dissipation process is really nothing else than the tensor modes excited waves that they dissipate, and it is an inefficient process because we know that gravitational waves go through the universe basically unimpeded.
So what are you saying? You're saying that the gravity waves are induced anisotropic stress, which is then
correct. Yeah.
That's got to be really small.
Yeah, it's 10 to minus 5 smaller than the scalar-induced gravitational distortions. That's the reason why the amplitude is not going to the same level as we might be able to see by direct constraints. but it's something you can calculate. And mind again, the window in terms of scales is actually a lot wider. The reason is because the gravitational waves, their source anisotropies continuously, and you don't get the exponential suppression of the window in terms of sensitivity. It's very interesting physics. I don't have time to really go into it. Okay, so I'm just looking at the clock, and I think I need to make sure that I cover some of the other, but we can do spectral distortion anisotropies now. This is another way of learning about energy release processes, and in fact, even things like Lightbird, Planck, and so on can put constraints on this. And details can be found in these papers. It's quite some new way of doing the anisotropic calculation. And here's just to convince you that we really do this. We can actually calculate the for different modes. We can calculate what is the spectral evolution when you have energy release on average or anisotropic heating. You can actually directly calculate how does the spectrum in different phases of the evolution look. And it's not just a sum of mu and y and so on, but it's actually some much more complicated, oscillating pattern that you will see. And by cross-correlating that with temperature anisotropies, you can actually learn about different phases of the evolution through the cosmic fluid. So this is really exciting, but I can't go into details here. Okay, one of my favorite last topics about lambda CDM is the recombination lines. How much time do I really honestly have?
We have.
So I have 20 minutes. Okay. So the recombination lines, you guys will, some of you might remember that that was one of the topics that I really was working on a lot while I was here. And it's really, really nice that we can now calculate these distortion signals from the hydrogen recombination plasma at redshift 1000 and helium and doubly ionized helium very accurately. So here's the prediction for these signals as a function of the frequency as we would see them today. So it's already the redshifted signal. And you can even see features from the Lyman alpha line, H alpha, and continuum lines, all these different bound and bound free transitions. They manifest themselves in broad spectral features that can still be seen. And the width of these lines, of course, encodes nothing else than the duration of the recombination process in all this, right? So this is really nice, but the signal is pretty small because we have so few baryons in the universe compared to the photons. But it has many, many features. So it turns out that even with foreground marginalization, at least in terms of sensitivities and so on, if you actually get to the mu distortion from lambda CM, you will also see the recombination lines, just because the penalty on foregrounds is only a factor of a few, because of all these wiggles that you can play with in terms of the foreground marginalization. So this is really interesting, and it opens ways, of course, to study really the recombination process. And I want to highlight a few aspects. So one thing is, of course, that recombination takes place in 3 phases. And if there's something non-standard happening between these different areas, this will reflect in the recombination lines. So you can directly test non-standard physics between the different recombination eras. And this is like something like 18,000 years after Big Bang, 130,000 years after Big Bang, and then 260,000 years after Big Bang. The last scattering happens at 380 or 400,000 years after Big Bang. So these are different epochs in the universe that you're probing. One thing to highlight is in connection with the Hubble tension. So you guys have heard about the Hubble tension. I don't need to tell the story. It turns out that there was this really nice paper by Niels Schöneberg where they did the H0 Olympics, and they basically compared different models or explanations for the Hubble tension. And some of the models that are winning are early dark energy related, incarnations of models promoting magnetic fields through their perturbations that they introduce into the medium, and then also coincidentally varying electron mass. Now, I'm not an advocate of this is the solution, but it was a paper that Luke Hart and myself wrote, and we showed that you can indeed, by adding this degree of freedom to the recombination process, you can really see that this, can alleviate the Hubble tension. So the interesting thing is of course, when you put that in and you ask, well, how does the recombination radiation change? Again, a calculation that I did with Luke Hart just last year, we showed that early dark energy will affect the recombination lines, in a direct way, because it stretches basically the redshifting between the different eras, and also the dynamics, and of course electron mass or variation of fundamental constant, fine structure constant, these things will affect the recombination lines. So again, you can actually test fundamental assumptions about recombination by directly measuring the recombination lines. That's one way to really shed light on this kind of scenarios. This is very interesting, and in a similar way, perturbations in the baryon density, which is one of the ways of explaining the Hubble tension or alleviating it with perturbations from primordial magnetic fields, in each of these patches that recombine at slightly higher or slightly lower baryon density, you get actually different response in the recombination lines. So if it's an overdensity, you get more photons, and an underdensity, you get less. And by averaging all this, well, the average is not the same as calculating the average distortion from average parameters. So you can actually see that these lines, they are the red, blue, and also the dashed gray line, they don't agree with each other. So you can in principle test variance contributions in the average recombination spectrum, which is again another thing that seems to be feasible with future incarnations of Pixie and enhanced versions of it. So this is also really interesting. Okay, so I think I made the case for these different types of scenarios, but now let's move on a little bit more into the synergies of spectral distortions. So the first I want to talk about is 21 centimeter cosmology and spectral distortions. So you guys have all heard about the edges detection or signal, right? And we can debate about this, but I don't want to go into details here. Explanations of it are just based on the simple formula where you can imagine one explanation increasing this parameter TR, the background radiation temperature, or one increasing the decreasing the spin temperature, so cooling the matter more. These are precisely, after the first result was presented, these are precisely the two directions that people thought about. And it's interesting because in connection with X plus cooling, you can imagine a spectral distortion. If this happens in early phases, you actually get spectral distortions from cooling effects, which Yassine Ali-Hamoud worked on quite a bunch. And he has also recently updated these constraints. A Pixie type experiment will be really, really sensitive to these kind of cooling processes, but I'm talking about the pre-recombination universe. So anyway, this idea is a similar one. So you have a cooling in the baryons through some extra coupling, really charged particles, all these things. Let me focus on the low frequency excess, which I think is a very interesting one, because we also have the so-called arcade excess. So arcade has in 2011 has measured, basically the absolute sky temperature, and has seen that there is some, excess of flux of photons, which apparently cannot be explained by just taking cumulative fluxes from all the radio galaxies that we have and so on. You can, when you do that exercise, you are 1/5 of this signal. So it seems like there's something going on, and it's also not just synchrotron that hasn't been properly marginalized over in our galaxy. So there's really some indication for a signal that's coming isotropically towards us. And the question, of course, is it primordial of origin? Maybe even some photon injection distortion. I'm going to actually show a scenario that works in a second. But bottom line is, if this is a puzzle that we know of, and it could be linked to the edges observation. So this is actually interesting to think about. However, Feng and Holder, who also proposed the idea of like the radio excess playing a role in edges, they also immediately said, well, if we just naively redshift back the signal to redshift 18, where the edges, absorption feature is originating from, or would be originating, then we can only accommodate 5% of this background. So the signal cannot be you can't just redshift back the arcade excess and be okay. You would overpredict the signal. So it's only 1/5 of the arcade excess that they advocate. However, they forgot one very important aspect, namely the soft photon absorption, which is happening if you actually emit this photon field. You will heat the medium, and if you actually put extra heating into the process, you will get rid of this constraint, and you can have 100% of the arcade excess already be present at redshift 18. So this is precisely what we did. We actually said, okay, let me assume that there is some injection of photons according to a power law, free type power law or a synchrotron type power law, with a time dependence that it wasn't really important, and I will show you in a second that we actually have another physical model as well. that now injects these photons in a physical way. The photons go through the thermalization calculation, and the photons at low frequencies are absorbed and thereby heat the medium through the free process. And when you include that heating, if you don't include the heating, you will get a signal that is, this one is actually multiplied by a factor of 5 to make it even on the scale. That would be 5 times larger than what edges has seen. And if you include the heating, you will get this red curve. So you completely avoid any of the, outrageous absorptions that you would see. So this is really important because it means that when you actually do this in a proper thermalization calculation, in an average distortion sense, you can actually make it work. And the absorption process that people neglect is actually really important in the formation of this 21 centimeter global signal. And it changes the conclusions that are reached from anisotropic constraints on this kind of level of radio excess that you could accommodate. So this is really important because it means that 21 centimeter cosmology and spectral distortions should be thought of together. Yeah? Okay, and this was just a toy model playing to show the soft photon heating process, because this is something that we realized a long time ago. But now we have done actually some specific model in connection with cosmic strings. And Chris, this is something that I was just reminded of when I was here as well, cosmic strings and superconducting cosmic strings as one source of spectral distortions. That's something that people have talked about. But here, we actually really performed a detailed treatment of the network evolution and how this emits photons into the medium and then thermalizes from redshift, very high redshifts to today.
What's the dominant emission process?
So these are basically cusps oscillating, and when you get the cusps become pretty, when the cusps go through this different phases, you get basically photon injection. And of course, there's lots of details of the real, treatment of this, and we have based our analytic description of the model on some simulations that were done with numerous, assumptions and so on. So this is highly uncertain physics, but not beyond doubt. But I will show you that these are the constraints that we get from CMB anisotropies and radio and so on. We can rule out this big wedge in parameter space. Yeah? And we did a detailed paper on this, explaining all the different, where they come in. And unfortunately, Virus itself does not do so much, but a Pixie type experiment would fill in this part, for example. Now, the interesting thing, and that was really the curiosity in some sense, I just said, let's switch and ask not constraints, but let's ask, is there a solution to arcade? And in reality, there is a small solution in the parameter space, which is not ruled out at this point. And this is really interesting because if you calculate the signal, you see that this is actually intriguingly good in comparison to a standard, fit, a power law fit. This would be the red line. And here, this is the signal that we get from cosmic strings. Calculated, just fixing the model, calculating, and then searching parameter space. So this is interesting, and it is a target for spectral distortion missions as well, because you can, in principle, at higher frequencies, see the emission of these cosmic strings manifest as spectral distortion, even in the CMB bands. And TMS is well posed to actually see this signal, and BZOO would probably also be able to say something about this, although it will become, given that it's not massively, that this looks like a quasi-power law, it might be more difficult. Nevertheless, this is really interesting because spectral distortion measurements could help you understand maybe the origin of this low frequency radio excess. And then, as I said, the link of the thermal exchange with spectral distortions and 21 centimeters is extremely crucial. Okay, so the elephant in the room, which Chris wanted me to talk about basically in the first minute already. So the foregrounds, right? Foregrounds is a big problem, but they are also an opportunity. So this is a synergy that I'm going to try to highlight with line intensity mapping and galactic science in general. So spectral distortions are buried under these massive foregrounds. This is the Virus sensitivity curve, and these are the kind of sensitivities that we're dreaming of within the next future incarnations of Pixie, Pixie Plus, and Voyage 2050, with the standard distortion signals that I mentioned today as well. If you deconstruct the foreground signal, then you have, of course, these multiple contributions. Here I'm showing, for example, the dust and the synchrotron, and here is the CO emission. And of course, a spectrometer will teach you about all these components and their average properties. So this is really great science one can actually do with the spectrometer itself, a clear synergy, and in return, other modeling of these signals will be an important ingredient for subtracting them in our task for going for the primordial signals. So one figure that I took from another talk from Marc-Antoine at a meeting in Tenerife, which is highlighting the great results that Joanna was actually presenting about 3D structure of dust. All this, understanding how we can use the information that we get from other observations that test, for example, the temperature distribution or the emissivity of these dust grains. This will be really crucial for understanding how to get to the distortion sites and how to use this and combine this and actually subtract things. That is really the goal that will need a multi-messenger, multi-probe, approach, and simulations will play a crucial role there too. And for the CO, the predictions for the CO monopole, they go all over the place. There's like factors of order of unity, but also factors of order of magnitude floating around, even 2 orders of magnitudes, depending on who you look at. And other lines also contribute. Here are some predictions from this paper, and it's obvious that these will all be interesting targets for a spectrometer. But it's also clear that they are not, at this point, constrained well enough, and so there's a big opportunity for both perspectives. One, the distortion perspective: how well can we model all this? How do we do this? How do we subtract it? Right, that's going to be really the name of the game.
So are you able to, with Pixie, cross-correlate or scale structure to remove some of this?
That will be one avenue for going forward. And Y distortion measurements, for example, just as a simple case, we will have Y distortion measurements and maps, and we will have also galaxy catalogs. We can, in principle, hope to even remove some of the low redshift Y distortion and therefore, drill down into the primordial Y contribution. Of course, it will at some point be very difficult to do this because you have the randomization Y as well, all these things. So, but I think with all these multi-messenger approaches, we can probably go 1%, I would say, of the average Y would be a not completely unfeasible target to reach, I believe. And that would, of course, then probe other regimes. Well, and of course, how do you even do this? How do you add this to the monopole exercise and all this stuff? So it's going to be a really big question, and a lot of work is needed there. And this is a great opportunity for everybody to actually really start contributing, because it's not totally dissimilar tools to everything that we're anyway using in CMB anisotropy science and so on. And then just turning it around, a spectrometer with these specs here is actually not that bad for even line intensity mapping. This is something, it's not the dream experiment in terms of frequency resolution, but it has a wide coverage of frequencies. It has a moderate angular resolution, 1 degree roughly, which means you can do the large scale intensity mapping, Y intensity mapping, if you throw that into the mix, but then line intensity mapping, of course. And this is meaning that you can even, with the spectrometer, learn things. And here's a compilation of some things that one could be thinking about. But most importantly, when you actually use a spectrometer from space and all sky, that provides you some completely different systematics on and angles on the problem. And with the monopole itself, you will learn something about the average ingredients that you normally are using to do the fluctuating part. So there's actually opportunities in both directions. One, the line intensity mapping community can certainly, with their measurements, inform some of the spectral complexity that one can expect, and the other way around, you can actually learn from a spectrometer something about what's going on in the astrophysical model. So this is really, I think, exciting, and is something that not so many people have been really exploring at this point, and I think a big opportunity to really go as well.
Could I just ask you about very low frequencies?
Yes.
So we get Brems and synchrotron, probably not so much synchrotron, don't know about the magnetic fields. Those are definitely secondary. My guess is you don't get a lot of that. There's a possibility of some of it in distortions.
Yes, so it has two aspects to it, what one should reply to this.
So,
So,
of course, referring to your 30 gigahertz cutoff there.
yes, so one of the things that we found in all the foreground marginalizations, if we were able to get better sensitivity at low frequencies, mind you from space, then we would be getting a much tighter constraint on mu. Why is that? Well, because the temperature, just the uncertainty in the monopole temperature, which has to be remeasured, is actually completely degenerate with the mu distortion at high frequencies. And only at low frequencies you can distinguish it. So you get a lot of leverage on mu by measuring the low frequencies. Now, going to low frequencies from space is very hard. So there's again a big synergistic aspect of like using low frequency measurements, potentially even things like SKA, at least to do mapping at low frequencies, or things like CITA, Quixote, all these activities that are extremely important also for CMB modes and their studies, because it will be very hard to do this from space. Now, direct free distortion signals, that is going to be another direction, which I would argue is going to be quite hard to distinguish again. But you could probably also, with maps of the hot gas and so on, you could again learn something. Okay, and the last point I wanted to make, because of course web ski is a big thing here, the role of simulations in all this will be extremely crucial. Because yes, some of these things we will measure, we will certainly get new ingredients observed, but some of it we just have to simulate and then actually demonstrate that we can really marginalize all the things. So one of the things we're setting up now is a spectral distortion foreground challenge, where we're going to precisely try to propagate everything that we at this point are talking about into the analysis and how this can be done, and hundreds of frequency channels with very high sensitivity and also moderate spatial and spectral resolution should actually be really giving lots of angles and handles on this. But it has to be fully demonstrated. Okay, so this is my last slide. I know this was a lot of different stuff, but I hope that I convinced you that spectral distortions generally are very interesting. The monopole science, it is guaranteed signals that you can go after. It's complementary. It can shed light on new physics scenarios, but also all standard physics. And it's really a lot of discovery potential associated with it. And it adds to any of the models that we're talking about with primordial black holes and primordial magnetic fields. All these things, spectral distortions can say something about it as well. Then I quickly highlighted that there's a synergy with the 21 centimeter cosmology. If you do not include soft photon heating, you will not predict the anisotropies right. Or you will at least conclude that things like the radio excess cannot be living at redshift 18, although it can in principle if you do it right. So this is showing that the calculations have to be consistently done, and there's a whole link of spectral distortion sources and 21 centimeter physics. Then the synergy with then the synergy with the line intensity mapping, or just generally the picture of like how can we actually learn about foregrounds and things like that. That's going to be an important direction, and lots of opportunities to do. To basically prepare for predicting what can a monopole measurement tell you about lines and their physics, or what can it tell you about the gas in our galaxy, and so on. And then the topic that I spent the least time on, and I just mentioned very briefly, but I'm happy to talk about it. There's also spectral distortion anisotropies at larger scales, which you can actually use to learn about cosmology. And these are not. We're not talking about outer power, because outer power is indeed very, very small, but you can have cross correlations between temperature modes and distortion modes, and these will tell you something about the early universe and what's happening. And they will be probably a way to distinguish different energy release scenarios as well with spectrospatial modes in the measurements. And I will stop there and hope I was not vastly over time.
Can we go back
How far?
anywhere in there, just in your imagination,
Oh,
to the issue of the high K
yes.
and the stuff that can occur that is not necessarily dissipating So we have a great interest here for reasons which are not obvious, but you put PDHs up there, but primordial non-Gaussianity is a big question because JWST requires something special. If you put in a bump at much higher than those caves that you're talking about, it's true they would be short distance things, but they would still be clustering in dark matter.
Correct.
And so the baryons would still respond, and early stars could be generated. So I think, but I haven't redone this calculation, that those curves have another curve, which is the reionization curve, which is basically a tau curve. And that the tau curve places a quite reasonable constraint on the higher caves than the one that you're targeting with Pixie and or with FireS.
Correct, and I mean, so one example is black hole accretion is in principle, you can constrain it with the existence of the black holes. When you then interpret these black holes as coming from primordial sources, then you can put a power spectrum constraint.
Yeah, but PDHs are a big stretch, right? Because the efficiency is so tiny.
Right.
That you have to do some very heavy tuning in order for PDHs to be just right, the porridge just right.
Correct.
But on the other hand, the impact of a high kind of bump, either in the power spectrum or better yet, with primordial non-Gaussianity as well, is that might well cover in the P of K thing, quite a distance at the high Kn.
Yeah.
And it's not included in these figures.
Correct.
And yet people have fooled around with it.
Yeah, but you also will understand that the mapping from the initial state to that final state that then allows you to interpret it as a condition, as an initial condition constraint, that mapping is extremely nonlinear.
Yeah, but not in a way that you don't understand.
Well, one can probably, I agree with
gravitational dynamics.
I
baryons coming in after.
Yeah,
And
yet
what kind of stars they create.
Yeah, yet we also understand that if we want to go to use, for example, dark matter perturbations at K of a few tens of inverse megaparsecs, a tenth, so whatever, 0.5 inverse megaparsecs, there's lots of nonlinear reprocessing that will not make that mapping so easy, and baryonic physics and so on. So I agree with you that we can in principle challenge these, get to that, but nonlinear physics is very, very hard to know.
Say your words in a different way. If I have to take them seriously, you throw up your hands and say, forget about understanding recombination because the gas physics is too complicated. But we aren't saying that. We're going after these signals. You're going after these signals, and we have to be able to compute them.
Well, I actually agree with you. It's too complicated to understand recombination. We better measure it so that we get it right and we don't misinterpret it.
Well, I'm not arguing against it.
So that's really the way to think about it. I agree with you.
There's a whole sector which is not on that.
Yeah, that is fair, but I mean, we can only do so much in terms of like the constraints that we can put, and we have linear physics perturbations here. That's the key thing that's really important, and it is definitely primordial physics because the mu distortion comes from a few months after the Big Bang. No reprocessing at later phases. So this is really key to the statement that I'm making. I agree with you that there's additional things one can do, and modes can be probed with 21 centimeter cosmology, for example, to way higher Ks as well. And the indirect things, as you're saying, is also correct. So for example, this is the line that I didn't explain here. Perturbations that are living here, for example, will source secondary temperature fluctuations, which then dissipate and can actually lead to mu distortion later. So the mu distortion window that's plotted here is actually conservative because it's probably stretching out like this in addition, and that's precisely the kind of things you're talking about. But the nonlinear reprocessing will be a harder thing to do.
It's not a negative.
No, I agree.
There's still a lot to do in exploring this space.
No, I think there's lots of opportunities, as you're saying. That's really key.
I asked just a really simple question.
Yes.
Which is totally not related to that. Just the few month time scale for the mu distortions.
Right.
Is that just when the photon generation process by a few
which is double Compton mainly. So double Compton is, because we have such a heavy photon-dominated plasma, double Compton is the main source of soft photons that then allow thermalizing. And in reality, double Compton and Bremsstrahlung are still active at low frequencies, even until much later, but they don't get transported upwards sufficiently enough anymore, and they don't get injected at sufficient rate to really do anything significant. So it's basically like the photons, they equilibrate everything at low frequencies perfectly to a black body of the electron temperature, but they don't get the transport to the high frequencies to fill in the missing photons. Yeah. So it's just that is what's happening. Yeah.
So how much spectral distortion science could be done by testing out in experiments that we're not seeing the monopole? We're only seeing a part of the sky, but there's some overlap here.
You mean really absolutely measuring?
Well, if you don't see the entire sky,
Right.
can't you still do some of the science?
Only when you have something you really compare your fluxes to, and you can in principle think of differential in frequency, where you say, oh, I don't want to know exactly what's my absolute, but I want to know the spectrum relative to it. You could in principle do that if you have perfect channel calibration, cross calibration, but that effectively boils down to measuring absolute. Because the channel cross calibration is extremely hard to do without such kind of thing as a calibrator on board. But yeah, I mean, in principle, yes. You don't need to go monopole. You don't need to measure really the full sky. You can in principle just integrate the heck out of, excuse my German, really integrate a long time into one direction.
Heck, the German word.
I didn't say it even.
Any questions? I don't think we have more questions online, so stand the speaker again.
Yeah, the small scale information propagation, that's